Good morning. It's an honor to present my paper in your respectable conference. I'm Rawan Elhalous and I'm presenting the axial compressive strength of steel members made of cold-formed angle sections. This paper will cover an introduction to cold-formed steel members, especially angle sections, a numerical analysis using abacus, then the models are verified according to experimental results collected by Dennis 2015. The angle column behavior is then presented, and the ultimate strength is compared to the ultimate strength obtained from effective weights method and direct strength methods. Steel constructions are of growing importance. Steel members are two families, hot-rolled and cold-formed. Cold-formed steel members are preferable for their high strength to self-weight ratio, ease of installation, and mass production. That results in less time consuming and cost savings. Cold-formed steel members can be used to construct buildings of 3 to 4 floors, stadiums, and airport hangars. Cold-formed steel members can be formed by bending of thin sheets by either roll-forming machines or press brake operations. Cold-formed steel members fail in three basic modes: local, distortion, and global. Local and distortion modes are characterized by entire deformation, whether translation or bending, of the plates forming the section. Popular sections of cold-formed steel members are channels, plane and lipped, angles, and sigma sections that can be built up back-to-back or two-to-two. Angle sections subjected to axial compression are widely used worldwide. Equal angles are used as web members in trusses, members of lattice transmission towers, and communication structures. Unequal angles are used as curtain walls. In the last decade, cold-formed steel members are the go-to sections in steel construction. But angle sections are not widely used, due to the lack of understanding of their true behavior. The reason that this presentation presents the behavior of equal and unequal plane and lipped angle sections subjected to axial compression. Angle sections are the simplest to form, but the most difficult to design, as there is no primary warping resistance, so highly affected by instability phenomena involving torsion. It was prevailed that angle columns buckle in local global and local global interaction. The reason that the columns are designed based on the local global interaction, which was then assured to be untrue. Angle sections, plane and lipped equal and unequal angles are examined in this paper, with angle dimensions 50 to 50, 50 to 30 for plane angles, with lip depth 20 mm for lip angles, with thickness range from 1 mm to 4 mm, and cylinderness ratio ranges from 30 to 120. Angle columns are attached to thick rigid plates at the ends to prevent warping, with local translation prevented at the corners of the plate and at the center of gravity of the column, where at one end the center of gravity prevents axial translation and the other end applies the axial force. Members are verified compared to the experimental results collected by Dennis 2015, with respect to the influence of different factors of initial imperfection obtained from the first eigenmode of abacus, which was torsion for short columns, flexure torsion for intermediate columns, and flexure for long columns, with factors ranges from 0.1 T to 1 T, where T is the thickness of the section. The experimental and numerical results are almost the same for 0.3 T, with F ultimate experimental over F ultimate finite element model ranges from 4 to 9%. Load deflection curves shows that increasing imperfection increase deformation and decrease the ultimate load for long columns. As for short columns, no remarkable influence of the increasing imperfection on a deflection, on deformation, or the ultimate load. The result shows that buckling modes of equal and unequal angles for short columns is major axis torsion, where two intermediate columns major axis flexure torsion and long columns exhibit minor axis flexure. Load deflection curve for lipped angle sections. Structure response is linear until sectional buckling, which is torsion or local. Then the horizontal displacement increases dramatically and the stiffness decreases up to failure. For plane angles, the stiffness decreases nonlinearly until failure. The deformation shapes show spread of yielding across the most deformed cross-sections that extend along the length of short to intermediate columns, that reflect the inelastic reserve capacity gained by columns. The figures shows the failure modes of equal and unequal plane and lipped angles for short columns with slenderness ratio 50. Plane angles shows torsional buckling and lipped angles shows local buckling. For longer columns, plane angles still shows torsional buckling until it reaches flexure buckling for very long columns. As for lipped angles shows local buckling until it reaches flexure for very long columns. Plane angles ultimate strength curve shows almost the same capacity for T equals 3 and 4 mm. That decreases 66% for T equal 2 mm and decrease another 60% for T equal 1 mm. For lip angles, capacity slightly decreases with decreasing the thickness. Ultimate strength curve for plane and lipped angles shows different profile. Unequal angle strength is higher than equal angle strength by about 10 to 20%. Increasing the thickness for plane angles has no remarkable effect on the critical buckling load. As for lip angles, increasing the thickness slightly increases the local buckling load and decrease the corresponding half wavelengths. The signature curves for plane angles shows no clear minimum for local buckling, as the section buckle in torsional buckling. For lipped angles, the signature curve shows clear critical local buckling. Increasing the thickness has no remarkable effect on the critical buckling loads, especially for plane angles, other than lipped angles. Effective width method is a traditional method of designing thin-walled members by redistributing the stress and giving a clear vision of the shift in the neutral axis due to local buckling. Effective width method depends on calculating the effective area. So the ultimate axial load is equal to the ultimate strength times the reduced area. The reduced area is equal to the effective width times thickness, and the ultimate strength is the smaller between torsion, flexure torsion, buckling, with the reduction capacity factor ignored. Direct strength method calculates the strength ultimate capacity by determining the elastic instabilities for cross section. So the ultimate capacity depends on the lowest of the critical buckling loads of local, distortion, and global. That is obtained by finite strip method using CUFSM program. Comparing the ultimate strength results from the numerical analysis and the effective width method and direct strength method shows inaccurate results, either safe or unsafe, with the plane angles results on the conservative side. The observation of the behavior and ultimate strength of equal and unequal plane and lipped angles shows the following remarks. First of all, the short equal plane angles columns are not sensitive to geometric imperfection values, and that the torsional buckling mode is dominant. Short-lived angle columns, the unequal angle columns, shows local buckling, while the equal angles shows distortional buckling. Deformation shapes exhibit spread of yielding across the most deformed cross-sections that extend along the column length of short and intermediate columns that reflect the inelastic reserve capacity gained by columns. Ultimate strength curve shows a different profile for plane angles than to lift angles. Thank you for watching.